Hi. So I'm Liz Jensen, and my presentation is going to be talking about this instrument development that I'm leading on the MOST mission proposal. And so this is an unusual proposal. It's really interesting, is that we are looking at putting four spacecraft up. Two are going to be holding quite a few imagers and other instruments, and then another two simply are part of this particular instrument setup, and they're moving adjacent to the others. So first question is can you see my pointer moving around?
Yep. Yes.
Yes. Okay. All right. So so you have what's the Lagrangian positions ahead and behind Earth, the L4 and L5 positions. And so we're talking about putting spacecraft here and here. The PI on this mission proposal is Nat Gopalswamy. And then ahead and behind of those positions would be the other spacecraft that would be hosting this specific instrument. And so this instrument we called FETCH, and it's looking for Faraday rotation effects transients and coronal mass ejections moving through the heliosphere. So you can kind of see where FETCH came from. And the interesting concept about this is that we are going to be working at frequencies that are fairly low. We're looking at between 20 and 100 megahertz. And at those frequencies, at these offset distances, you can see the solar corona in there. You get a measure of the integrated density. You can get a measure of the integrated magnetic field that is parallel to your line of sight. And then you get how those change. And I'll also talk briefly about how it's possible to also get velocity measures that are average, that are in the line of sight, but kind of averaged as well. And so, so first of all, there's certain aspects, and so I'm going to focus on coronal mass ejections. And there are certain aspects of this instrument that we are capable of measuring, and coronal mass ejections really encapsulate a lot of these different kind of phenomenon that we're interested in. So the first thing is that if you have four spacecraft up there, you end up with these four different lines of sight that you can pass through the corona upstream of the Earth. And this furthest line of sight out here, that lowest offset to the sun, this is located at 0.5 AU. And then this line here, I've set at 30 solar radii from the sun. So you get an idea that you can get this measure of the evolving structure of your coronal mass ejection, and as well as other structures. So you can also see on top of this, there's a CIR, and that's a co-rotating interaction region. So you'll have slow and fast solar wind, and so as they interact with each other, you develop these structures. And so with the coronal mass ejection, you have upstream features, you have a shock, and there's also what you have the sheath region, where if you think of like a snow plow, you end up with this concentration of density upstream of your magnetic, your strong magnetic flux rope that's in this core where you have less density. And one of the issues that comes up is between observers and modelers, there's this self-similarity between the width of the sheath and the width of your flux rope. And so modelers say it has to pancake, and observers will tell them, well, we're not exactly seeing these classic pancaking features that you're modeling. So that's an open question there. There's also going to be MHD waves throughout the structures and throughout the heliosphere, and they have different characteristics. So the MHD waves here in the sheath region are going to have different characteristics to MHD waves that you would observe in the slow solar wind, or in the fast solar wind, or in the quiet solar wind, or in the active solar wind. That you're going to have different kind of wave transfer conditions that are different. Because we are measuring magnetic field, you can take your flux rope model and you can calculate what the flux rope orientation would be in order to produce that type of Faraday rotation, which I'll show you an example of. And then there's also on the back end is you're going to have turbulence that occurs as the field lines, you have this strong structure that's plowing through at high velocity. And then on the back end, you have this highly perturbed plasma that happens behind it. And in this region, we observe some reconnections. So it's a really interesting region for your plasma physics and dynamics and understanding how does that affect the evolution of the structure. Okay, so walked you through that. All right, so let me show you kind of what we would see relative to this instrument and what kind of data it would produce. So do you see this? Is that visible?
Right now I see sort of a full page, and then as you zoom in, the bottom kind of goes off the bottom of the screen.
Okay, let me try that again. Okay, it stopped running the GIF. Is this too small for you? Is that visible?
Well, we see the see
Yeah,
the shape of the
it's
curve.
fine.
I can't read.
Okay. All right. So here we have a simulation of the CME. So the image that you saw before was out of the simulation that was conducted of a 2005 CME in May by Chip Manchester. And so here we show his model with the CME crossing the different lines of sight. And so we have the spacecraft. And so I have spacecraft 3 to 4 and 1 to 2, and then 1 to 4, and then 2 to 3 going across this way, or 3 to 2 going across this way. And so one of there are certain things to understand relative to what I'm showing you in this animation is this amount of Faraday rotation, it's dependent on the frequency. So if this frequency shown here is at 80 megahertz, so if I go to 20 megahertz, it's going to be that much bigger. And whenever I talk about Faraday rotation later, one of the issues is you're rotating around a circle is there's a plus or minus pi ambiguity. So are you in the first quadrant or in the third quadrant? And your frequency allows you to bear that out. And I'll talk about that in a little bit more. And so what you can see is that the structure first crossed that line of sight closest to it at 30 solar radii. And then as it moves across the other lines of sight, you can see these similar kind of structural behaviors relative to the magnetic field. And it's weighted by the density, which I'll get into. And you can see that there's a timing issue is that here you see it first and then it gradually propagates across the other lines of sight. And this is the information that we would be able to pull out is how is it evolving as it moves out in space. Okay, so let me get back to the presentation. Okay. All right, so relative to your flux rope, let's see. Okay, so if I want to show you a kind of flux rope, I'm going to stop the screen share very briefly and show you what I've got here in my hands. So, okay. So not everyone buys into this relative to magnetic flux ropes, okay? But the idea with magnetic flux ropes is that the magnetic field is balanced, so it's called force-free. And these are idealized, of course. And so you would have the magnetic field in the center of the flux rope oriented straight up and down. And then as you move out in radius, the field gets increasingly twisted. And one of the things is that you have a dense collection of magnetic field lines in the center and they want to push out. A twisted magnetic field line, it doesn't like being twisted. And so it wants to straighten up. And whenever it's trying to straighten up, it's pushing inward. So you get this balance of forces. And there are different kinds of orientations relative to this solution. You have the left orientation, the left-handed orientation, and then you have the right-handed orientation. And I noticed this, and I have no idea why, but all plastic slinkies are left-handed and all metal slinkies are right-handed. Just one of those things. But nevertheless, in this figure that I'm about to show you, you got to picture the slinky, your flex rope sticking out of the page like this. And the solutions that are shown are for a right-handed flex rope coming out. And so you have your line of sight and your slinky is going to be moving across your line of sight. And so you see this twisted magnetic field first as it goes across your line of sight. And then the component in the middle is perpendicular. It's that perpendicular component. And that one, if your line of sight is like this, and then the magnetic field like this, then it doesn't see anything because Faraday rotation is only the component parallel. And then out the other side, you'll see the other end. But there's a number of different orientations that you can do for this, and I show all of them in this following screen. Okay. So, hopefully the share screen, hey, it still works. Okay, great. Here we go. Okay, so here are all the solutions. And the one that I showed you was right here. And if my line of sight's going this way, and then the right-handed orientation is going this way, what happens is that the magnetic field is moving against my line of sight. So it starts out negative. So this is the solution that I was talking about. And then as this part crosses the line of sight, the component of the magnetic field's this way, and that is parallel to your line of sight. And so then it is positive. So it makes what I call a sigmoid feature. Now I'm assuming that density is constant across this, and that's not necessarily the case. And that's why you want to fit your magnetic field, your CME model to the Faraday rotation observations. But this gives you some pretty clear information about what the tentative orientation is. How would you initialize your model? And then here, this is looking down the axis. Here, the axis of the CME is along the line of sight. So it's rotated, you're looking down the pipe. And then here it's rotated and it's opposite the line of sight, it's anti-parallel. So that's how Faraday rotation is going to give you your magnetic field information. Okay. So one of the issues is that we're going to be looking at is one of the theories is that the flux rope is eroded by the sheath. And so we can track that and see relative to fitting that flux rope solution to, to the observations. With the erosion of a force-free flux rope, what happens is that it gets less twisted because the twisted lines on the outside get reconnected and taken away. And so it will become less twisted as it moves away from the sun. That I already mentioned the self-similar issue, you know, with how is it that the sheath of the flex rope and then the flex rope itself somehow do not pancake as much as is modeled. And another thing that we need to address is that Faraday rotation is weighted. So that component of the magnetic field parallel to the line of sight is weighted by the density. So there's more density closer to the point of close approach. And so that gets more weight to your solution. And so, you know, how do you separate the variables? And we can do that with white light observations. And then, oh, I didn't take that out. We can do that with white light observations, but then there's also other ways to do that. Okay, so Other concepts that we're going to be examining is that you can see it clearly whenever it's time to start talking about what kind of MHD waves do we expect. And so whenever I showed you Chip Manchester's solution to the 2005 CME, it has an estimation for the MHD wave energy, but as to exactly the nature of the fluctuations, that was not modeled. So we would, our data would absolutely be seeing these kinds of fluctuations. We would see fluctuations in polarization angle, and then we would also see fluctuations in frequency. Now, these fluctuations in frequency, that is information that gives you about the total electron content along the line of sight. And so that enables you to start to separate how much is the magnetic field contributing to your observation and how much is the changing electron density contributing to your observation. And so, let's see. Okay, so whenever I mentioned about reconnection, that's specifically relative to a discovery that we made in 2018. So here you can see on the bottom panel right there, that bright spot, that is the planet Mercury. And at the time, Messenger was in orbit around Mercury. And so while we were conducting these observations, the solar wind released a coronal mass ejection and it crossed our line of sight. So whenever the dark core area where you expect to see your strongest magnetic field, it had that sigmoid feature. And relative to the sigmoid, there's a degeneracy. So it could be left-handed oriented northward, or it could be right-handed oriented southward. And so in order to separate those, you need some more information. So that's why there are two solutions plotted here. However, what we didn't expect is what came up behind the CME. So after the CME passed, we saw what's here is that this is a map how linear the signal was. And spacecraft signals, to save power, what they do is send mostly circular polarization. So you can see that here is that we had roughly 1% of the signal was polarized linearly. So, so that was basically the leakage. But we were able to observe the leakage and get our polarization. So it was elliptically polarized, which was fine. However, whenever the CME finished crossing the line of sight, there was a structure that literally changed the polarization of the signal. And so you know that the signal that's being transmitted is not changing polarization. It is the same, mostly circular polarized signal that you expect. However, what we were measuring at the antenna was significantly more linear than what was being transmitted. And so that's a form of mode conversion. And the signal was mostly right-handed. And so somehow we ended up with more power in the left-handed mode relative to the right-handed as the structure went through. And it was a bit of a mystery because the density in the solar wind at this location and the magnetic field in the solar wind at that location, in order to get mode conversion the traditional way, you need to have a really high density or really high magnetic field strength. And that just was not physically possible. I mean, we would have had to increase by orders of magnitude in order to get this kind of mode conversion. And so whenever I went and reviewed the equations, I determined that it was a strong electric field, a particularly strong electric field in order to do that. And the only structure that I know of that has a very discrete, small, strong electric field is reconnection region. So we are assuming that this is a bursty reconnection occurring on the backside of the CME. All right. But this is something else that you're not going to find in Chip's model. But this kind of stuff will be present in the data whenever, you know, it gets approved and launched, like all proposals do. Okay, so remember how I said about the 4 lines of sight? what we can make the argument that actually we are looking at 8 lines of sight. And that's because the light time in order to cross from one side of the so you've got the Earth's orbit at 1 AU in the ecliptic, right? To cross from Lagrangian 5 to Lagrangian 4 or vice versa, that takes roughly about 14 minutes. And then the other line of sight that's closer to the sun takes more like 16 minutes. And so what happens is that is a significant chunk of time in which the photon that's been emitted is going to be traveling through the plasma. And so what I show here with the simulation is I put a discontinuity in it, but a change in speed. But basically you have a signal that's being transmitted from line of sight 2, and this is line of sight 1 over here, and then this one is transmitted from line of sight 1, and it's traveling to line of sight 2. Well, this is a line of sight shown in blue. The plasma that's actually crossing the line of sight at the time that the photon is passing through is shown here in this plot. And I changed the velocity. So here in the lower velocity, that was about 200 kilometers per second. And then here in the higher velocity, that was about 400 kilometers per second. No, I'm sorry, 300 and 500, it's 300 and 500. And so you can see is that distinctly different types of plasma is being sampled at any particular time. And so it may be possible, we're looking into this to see if there's kind of a grid lattice that you can look at and do correlations in order to be able to start breaking down your line of sight and not have to and be able to start to decouple your integration, the integration effect of your weighted measures between both the TC and the Faraday rotation. So so that's another possibility with this particular instrument. So this shows kind of what happens in the simulation from Chip's model. So if we compare between spacecraft 1 and 2 and 2 and 1, so you can see the time in minutes. So this is a significant chunk of time, several hours. What happens is that you've got some observable changes in your Faraday rotation, differences in your Faraday rotation at low frequencies. So this shows 10 megahertz, but I'll explain why we're looking at 20 megahertz. Okay. All right, so for total electron content, I mentioned about how the frequency is going to be fluctuating. And normally, whenever you think of wave propagation, you're not thinking of the frequency fluctuating. It's going to be the index of refraction is affecting your wavelength. However, whenever you are at your fixed antenna, what appears to be fluctuating is the frequency. And so I call that the apparent doppler, which is a plasma effect. And so at the time that this figure was made, I called it Doppler tracking, but now I call it apparent Doppler. And to compare, can you get total electron content off of this? I did fit it to the ranging data, which travels at group velocity, not phase velocity. And so you can see that relative to the change in total electron content, it does a relatively good job. The only issue with using apparent Doppler tracking is that this initial point, whenever you first start, you don't know where it is unless you use white light data or something like that. Then otherwise you have to set it at 0 and then just check how it changes. Ranging, so this is the phase velocity of your signal, and that affects the frequency that's ultimately observed at your antenna. Ranging is based on the total the arrival time differences of wave packets. So it's traveling at group velocity. And while it's entirely, we are capable of enabling this on the antennas, the current issue that I'm grappling with is that, as I'll discuss here in a little bit, we can measure down to microseconds. However, because of the signal to noise ratio, in order to get a nice strong signal to noise ratio and reduce how much data we need to download, what happens is that we end up having to integrate as much as 10 seconds. And so how do you find a microsecond change with a sliding 10-second integration window? I'm trying to simulate this, and right now I'm not very optimistic that it's going to work. And so what we're probably going to do in order to get this total electron content is that we will be doing the apparent Doppler tracking and then pair it with white light observations, because there will be white light imagers on the spacecraft that are in the Lagrangian points. Okay, so I have been tantalizing you with Faraday rotation, telling you all about what it does. Here's the equation. So this is a constant, and it's based on your plasma conditions. You can see that right here. And then Faraday rotation, it varies with frequency squared. And so how much your signal rotates depends on your frequency. So the lower your frequency is, the more it rotates. And how I said it was weighted, so it's the component of the magnetic field parallel to your line of sight, and then it's weighted by density. And so you need, so if you're measuring total electron content, you would basically take B out of the picture and you'd be integrating N times DS. And then there's also a frequency, it varies with 1 over frequency, but not frequency squared. So, so there's you can do some decoupling of the electron density with that. However, based on my analysis of the simulation, is that you will still have artifacts in there. And so it would be better to use the 8 lines of sight to do your inversion as opposed to necessarily the 4 alone. Now, a lot of times whenever people are talking about Faraday rotation, what they'll do is, because they're observing across different frequencies, and that's what we plan to do as well, is they'll talk about rotation measure. And what that does is it basically takes Faraday rotation and then has it divided by C, which is constant. And so that way you can compare how much rotation you get between the different frequencies. Whenever you go to actually measure your Faraday rotation, that is going to be Faraday rotation, and rotation measure is a kind of a normalization calculation. Okay, so I just wanted to emphasize relative to Faraday rotation is that it is weighted by density. So here's a line of sight and it's offset. And you can see here its minimum offset. That's also where you coincidentally will have your largest densities. Whenever you have a CIR, you can get some pretty good size densities over on the limbs if your CIR happens to be close to the limb. But ultimately what happens is that with your Faraday rotation signal is that you're integrating it, right? So you start out at 0, and then in this particular simulation, it goes negative, it's rotating negative, and then as it hits the magnetic field that's parallel to the line of sight, it goes from negative up to positive. So ultimately, at any point in time, you're measuring this final value of the plane of polarization of your signal. So it's entirely possible that with your lower frequencies, it could have rotated through over, you know, that pi that I was talking about, the plus or minus pi ambiguity. And so that's why you want to have your Faraday rotation observations at more than one frequency so that you can address this. But at the same time, you don't want to just go for the high frequencies because those are harder to resolve. So if you really want to resolve the angle of the rotation, you want to do your low frequencies. But in order to unwrap it and avoid that pi ambiguity, you want your high planopolar, you want your high frequency. And so the way that I like to describe it is that, you know, with your microscopes, you have the coarse, you have the control that you have in order to shift the plate up and down so that you can focus. Well, you've got a coarse control and then you have a fine control. And so the high frequency is a coarse control and then the low frequency is a fine control. So it's one way of thinking about it. Okay, so now, whenever I said that the Faraday rotation would fluctuate, you're just looking at the final value. Here I show low frequency Faraday rotation, so it's at 10 megahertz, and we're just going through pure changes in structure. So I'm not changing the magnetic field or anything, I'm just changing the density with time. And I was using this calculation that Bernie has. He uses a model to, Bernie Jackson from UCSD uses a model to fit to scintillation observations that Nagoya University is making. And anyway, so you can see that with this low frequency, the fine knob, you can track these kind of changes in the structure. But one thing to keep in mind is on top of that, you have all of the MHD waves, which are causing all of these significant fluctuations. So this is kind of like, this is going to be this background sloping that's that happens to be crossing your line of sight. But on top of that slope, you're going to have these huge fluctuations just from the MHD waves. Okay, velocity. All right, so let's see how this pulls out. Okay, so you can get velocity along your line of sight, like the way I talked about. You have your magnetic field, you have your density through total electron content. You can also do your velocity by looking at characteristics of that frequency fluctuation. So not only can you use it for density, but how it varies with frequency, you can also use to calculate velocity. However, getting these kind of measures relative, you can see the frequencies are here, that, and they're really relatively low, is that to get these measures on the velocity, you end up having to get to relatively high sampling frequency. And remember, I told you that we are looking at having to integrate more around like 10 seconds. So there's another way to do it, is that if we have characterized the solar wind for different regions, and that we kind of know what is a common frequency for a certain type for solar wind going past our lines of sight, we can talk about characteristic velocities and characteristic wave numbers for those fluctuations. And then we can do a spectral analysis with that by projecting off of, oh, here we go. We can do a analysis off of those fluctuations and say, okay, this is our characteristic wavelength fluctuation. And so based on that, the velocity that we predict for, if we assume our flux tubes or magnetic flux tubes are a certain size, then we can get this relationship and calculate what is the velocity of solar wind crossing that line of sight. So it's got error bars on it. You can see there are error bars on top of that assumption, but nevertheless, it's an extra bit of information that you can use for further analysis. And we would have more accurate velocities just simply because it's crossing the line of sight at one distance and then crossing the line of sight at another distance. However, if we also have kind of more of an instantaneous velocity to compare between them, we can track a little bit more on the nature of its evolution as well. Okay, so let me go back here. Okay. All right, the instrument. Okay, so I've been talking about all these wonderful measurements that we'll be making. Let's talk about the instrument. Okay, so you want to fly an instrument that is got some history to it. And what has already flown before is what's called this Forte mission. And you can see that you have this cross dipole antenna that extends out for roughly 10 meters. And, or is it 12 meters? Roughly 12 meters. And what this is called is a log periodic antenna. And this is what enables you to measure across a breadth of frequencies. So if you want to measure from 20 megahertz up to 100 megahertz, a log periodic antenna is one of the first type of fractal antennas. It will let you do that, but they are big. As it goes down in frequency, they get bigger. And so that's how we ended up with 20 megahertz being our limit, because relative to this particular design, 10 megahertz was going to break the bank. But if we have this extent being 15 meters, which is feasible considering this particular model that flew was 12 meters, we can get down to 20 megahertz. And so based on our initial calculations, that will not have too much of an impact on what we ultimately are capable of measuring. What's interesting about this particular antenna is that in the stowed position, it's very reasonably sized for fitting on top of, for fitting within your launcher. So it's 0.5 meter in this direction, and then 0.45 meters on either side of this cylinder that holds the antenna. And so let's see, the company that originally built the antenna, they got taken up by Northrop Grumman, I believe. And so, so did all their notes relative to how this was constructed and flown. And so we are working with them on adapting this for our particular conditions. Now, what you'll see here is the reason why I talked about our signal to noise ratio having to require a longer integration time is we're transmitting a signal across 2AU. Well, it's relatively straightforward to send a signal across 2AU or further if you've got this really big antenna on the Earth with a huge collecting area and as much power and resources as you need to go and sit down and process the data and pull out that signal, even though you've got a poor signal to noise ratio. Those are not conditions that we have for this particular situation. And so what's interesting is that the gain is expected to be around 6.5 dB at the lower frequencies, and then greater than 10 dB at 60 to 90 the higher frequencies. Okay. One of the issues is that whenever we first showed we were briefly considering a dipole model for our antennas, and we got some significant pushback from the radio community because dipoles transmit in all directions. And so this particular antenna, it has a beam width of 30 degrees, and that's at the higher frequencies. It gets broader at the lower frequencies. And so let's see. Yeah, so here you can see the integration time. Here you can see the frequency. Transmission power, we're looking at pushing out 100 to 200 watts through the antenna. And then aside from that, it doesn't need special temperature for operations. Now, whenever it comes down to the signal and how it's handled, this is really complicated. So when we're looking at 4 different spacecraft, each of them sending 2 different frequencies. And so we need to offset the frequencies so that we can distinguish. So if you've got one spacecraft and it's looking at 2 other spacecraft, which each are sending separate frequencies, so that one spacecraft's going to see 4 different frequencies coming in, there needs to be some offset so we can distinguish which spacecraft they're coming from. Because as you can see with the cross dipoles, there's not exactly a whole lot of pointing that you can do with that. And so then also on top of that, there's transmitting at those frequencies. So part of the spacecraft design that we came up with is that one frequency, so for example, here we show some of the lower frequencies, they would be transmitted at a horizontal polarization. So it's got this, continuous polarization. It's got this fixed initial polarization that's transmitted at. And then we have the higher frequencies getting transmitted on the vertical polarization. And then whenever you go to observe the signal actually arriving, you got to turn off the switch and look at both polarizations, because that's how you track the rotation. You need to measure both the horizontal and the vertical in order to figure out what the orientation of your signal is. This is the system that we're currently looking at. And whenever we broke down the information that we're probably going to need to download, I put in that we would be looking at collecting FFTs, the full spectrum, once every hour. And then aside from that, for the rest of the time, we'd be pulling out specific points of interest out of the FFT. For the rest of the time. And so what I came up with is relative to the downlink speed for the stereo spacecraft, then we would be looking at maybe 4 minutes thereabouts per day worth of downloads. So if we only get a download pass every, if we get a download pass every other day, out of all 4 spacecraft, it would take 10 minutes of that downlink time to download our data. And that includes housekeeping. So as you can see with the system, every single connection is a potential point of failure. And so we would need to collect some information on that just to make sure that everything's operating normally. All right. And that's the end of my presentation. Any questions?
Yeah, I have a question. So, not being into this at all. So what is if you can back up a little, what is the overarching goal of this? Just to get a better understanding of how the solar corona works? Or do you have specific science questions you want to answer?
Yeah, so the specific science questions that we're trying to answer is so if we take the case of coronal mass ejections, what we want to know is how do they evolve as they propagate towards the Earth? There's a significant amount of variety with the different CMEs and the characteristics that they have. And so some of them are very geoeffective and some of them are not so much. So in that sense, you could say, why should I care about this? That would be a space weather type of explanation for that.
Okay, thank you.
Yeah, sure. I mean, the other thing is that how the solar wind evolves, you can see that its characteristics change roughly around between 30 solar radii and 0.25 AU. It goes from these kind of clear striations into a more bumpy, poofy kind of like structure. And so how is that evolution taking place? What's going on with the turbulence evolution? Those are some open science questions that we would be able to answer.
Liz, I missed part of your the beginning. When would this be submitted? When would it fly?
Okay, so we are working on getting these details close to final in time for the decadal survey. They haven't officially requested white papers yet. We don't know in what format they want them or what the page limit is, but we're aiming for the decadal survey that's supposed to be announced this month. And so I think that these white papers need to go in maybe around April. And so if we can convince, the decadal community that this is a priority to push this mission forward, Gopal saying, we're looking at maybe around 2030.
Would there be opportunities to perhaps fly this instrument earlier, on some other mission?
Yeah, so if it gets prioritized, it could get flown earlier. And Gopal's already talking about de-scoping. So he's saying that if instead of having fixed spacecraft at L4 and L5, we could have them just kind of move between those two positions. You can see that there's two positions on either side. If we just have them move between those positions, we can get a lot of data. And so you would have to make a number of assumptions whenever you're doing your calculations for how things are evolving. But still, if it's up there for several years, you would get to have a pretty clear idea as to how things evolve at different offset distances. So he's already talking about that.
Are there any foreign agencies that are pursuing this kind of work?
Yeah, the European, well, not really. Nobody's really touching Faraday rotation. So this is the first one that's really going after it. Although Angelos Verlides has expressed an interest. He's like, we're going to see how your instrument goes, but he's also interested in the Faraday rotation concept. And I mean, there's really no other way to get these magnetic field measurements. I'm sorry, what?
Where is he? I don't know. I don't know the name. Angelo Verlides.
Angelos, he's in the Northeast, and I'm not sure if he's with headquarters or if he's with Goddard, but he's definitely in the
okay. He's not with ESA or the Russian Space Agency or something like that.
No. But ESA is flying a mission soon. It's due to launch maybe in the next couple of years. That does go to the Lagrangian positions to do regular observing of the sun. So they did pick up on that idea of going to the Lagrangian, and Gopal's just, kind of taking it, to another level, saying, hey, let's do these Faraday rotation measurements, once you get into that position.
Liz?
Yeah.
I thought that there were some Chinese investigators that were also looking into the Faraday rotation.
I am not aware of that. So you've heard something?
I thought they published a paper on some observations or analysis of some observations. I don't know that they're necessarily launching a spacecraft, but I was thinking of the paper.
Okay. Well, I'd like to know more. Is it kind of like ground-based? They're looking at a spacecraft that's in orbit, kind of like how we've traditionally done it?
Yeah, I think that may be more likely what they did. I'll find the paper and send it to you if that's the case.
Okay. Thank you.
All right, any other questions? Well, thanks, Liz. I'm glad we finally got to do this. And it looks like next week we may have an applicant. We haven't heard back yet.
Yeah. Great.
All
Thanks,
right.
Liz.
All right. Thanks, y'all.
Bye, everybody.
Have a good one.